Hello, am I audible? Hello, we will start at 6:05. No, all of you. So it is 6:05 now. So I will start. So is my screen visible to all of you? So welcome all of you to the week 11 of live session of solid mechanics course on NPTEL. My name is Manoj Shikhar. I'm one of the TAs in this course. I'm a PMRF scholar at IIT Delhi. I work under Professor Ajit Kumar and my department is Department of Applied Mechanics. I have done my BTech and MTech from IIT Kharagpur, and in these live sessions, I will try to solve your doubts. So if you have any doubts or any question in between, or while I will be solving some numericals, or if you have some other doubts from previous weeks, you can ask me. Now, I'd like to declare one thing, that we are not supposed to help you with the assignments which are active right now. So please refrain from asking any questions from the active assignments which are on SWAYAM portal. So now without further delay, let's start this session. So in this week, Sir has covered energy methods. The subtopics which are included in energy methods are principle of superposition, reciprocal relation, Maxwell-Betti-Rayleigh reciprocal theorem, Castigliano's first theorem. Then in the last lecture, Sir discussed extensional, bending, torsional, and shear energy. Then we found out the total energy of a beam, like the generalized energy. Then we found like the displacement using some generalized dummy force. And then we also saw how can we find the reaction or support load. So I will be first going through the PDF of the week 11, and then we will solve a few problems. Now, for the notes of this course, solid mechanics, which is happening on NPTEL, you can go to the link mentioned below. So this is the notes which is for APL 104, the solid mechanics course at IIT Delhi, and the same are being followed on NPTEL. So if you have any doubts, you can revisit these notes and you can get it cleared, or you can write on the discussion forum of SWAYAM portal. Also, these notes, they have some questions at their end, and those questions are at the level of competitive examinations. So if you try to solve them, you may be able to get good marks in the solid mechanics portion of the competitive examination. Thank you. Sorry. So the course which we are studying right now, here we are studying the linear elastic solids. So the superposition of displacement will work in this case. So keep in mind, because this is a basic course on solid mechanics, we are able to use superposition principle. Because we are at the end of the course, almost at the end of the course. So I just want you to remember this, because in future, if you take some advanced course, there the relation between displacement, strain or stress, they will not be linear. So there you cannot use the superposition principle directly. But for this course, superposition principle will be valid. And it actually helps in lots of engineering problems. Even in GATE, you can use superposition principle in most of the cases. But if you read advanced solid mechanics or continuum mechanics or advanced finite element methods, there we do not use superposition method. So in superposition method, what we do, we find displacement due to each of the forces and we add them. So sir has discussed this in a very extensive manner in his video lecture. So I will skip this part. There are few things which you should remember. There was one interesting thing which sir had discussed here. Maybe I can just reiterate that here. So in this case, what was happening? First, we applied a force F1. So we wrote the displacement delta 3 that will happen solely because of F1. So it was K31 F1. Then we applied F2. So delta 3 now will have the displacement due to F1 plus what is the displacement happening because of F2. Then we applied minus F1. So the net force on the body became F2. Okay. So we know that the deflection due to F2 will be delta 3 equal to K3 to F2. And from equation 10, 11, the difference will be that in delta 3, there will be one more extra term, K31 prime, double prime minus F1, right? So equation 12 and 13 should be equal because essentially we are applying only F2 in this on the body. So if you equate this, we get equation number 14. And from there, we argue that since this is true for any F1 and F2, the coefficients of F1 and F2 should be 0. And from there, we get K32 prime equal to K32 and K31 equal to K31 double prime. So this is the superposition method. This is the alternate way to prove the superposition method. Okay. Another interesting thing was that we wrote energy stored equal to half kx square. So if we apply a force slowly, like from 0 to F, if we go, then the total work done will be half into F into X. As you can see, it will be the area of this triangle. But if you suddenly apply the force, then the force versus displacement graph will look something like this. It will look something like this. So we are applying a force F1 from the start. So in this case, total work done will be total work done by force F equal to the area under this curve, right? So this is the area. So what is this? Suppose this point is X and this is 0. F into F dot X, basically. So from here we can say Fx. The energy stored in the body will still be half Fx square. Sorry, half Fx. In the body will be half into Fx. Okay. One more interesting thing was that, and actually I want to discuss this because I've seen many of my students making this mistake. So, so initially we are applying only force F1 on this body. So this body gets deformed. Okay. And we write energy. So the energy stored in the body will be half into F1 delta 1. As we discussed here, the energy stored will be half into F into displacement. Okay. So we can write half K11 F1 square. You can replace delta 1 by K11 into F1. Now we are applying F2. Now we are applying F2. Okay. And because of F2, there will be some displacement at 1. There will be some displacement at 1. So the energy while writing, while after applying F2, the energy stored in the body because of deformation at 1 will be F1 into delta 1. Okay. So this delta 1 is like the new deformation of 1 prime from 1. So 1 double prime. So this deformation which is happening here, initially F1 is already acting. So this is a case like this. F1 is acting from the start of the application. So that's why the total work done by force will be F into X, and that is what will be stored in the body. Okay, so that's why F1 into K1 to F2, and the energy stored due to F2 will be half K2 to F2 square. So keep this in mind. Like people, what they do, they will write F1 in, they will write energy equal to half F1 delta 1. And then after the application of F2, they will write half into F2 into delta 2. They forget about this term. So you should not forget about this term, and also remember that here half factor will not be there for this case. Okay, because F1 is acting from the start. When you are applying F2, F1 is already acting upon the body. So F1 is acting throughout the new displacement which is happening from 1 prime to 1 double prime. And then what we did, we again we did the analysis by first applying F2 and then applying F1. So from there we have equation number 24 and equation number 26. On comparing, we find that the last term K1 to F1 F2 and K21 F1 F2 is different. But since we are using the linear elastic body, so the final energy stored should be equal. Hence, K12 must be equal to K21, and thus Kij equal to Kji. So this is called reciprocal relation. Now, Castigliano's first theorem is that if we know the energy stored in the body, so we can find the we can find the displacement. We can find the generalized displacement at ith node by differentiating it with respect to f at that node. Okay, so E equal to half fi delta I. So we can replace delta I by this term and we will get expression like this. So this is what Castigliano's first theorem is, that the corresponding displacement delta K is the derivative of total energy with respect to the corresponding force Fk. Suppose if I tell you that find the corresponding displacement theta K with respect to the corresponding displacement theta K. So what we will do, we will have to differentiate this E with respect to Mk. Mk is the moment. Okay, so that is what we will have to do. Then in the next lecture, so in last lecture, we were introduced that we can find the displacement or the generalized displacement of a like delta K by differentiating our energy with respect to Fk. So how to write total energy, that is being discussed in lecture 30. Okay, so how do we write the total energy E? So while writing the total energy, we have to take into account all kind of forces and moments which are acting on the body. Or in other sense, we have to write we have to take into account all kinds of energies like extensional energy, bending energy, torsional energy, shear energy due to transverse load. So we know that it doesn't matter if the it is a linear case or non-linear case. Energy is always additive, so we can always add the energies, right? So this total energy finding method is not necessarily only true for the linear elastic body, but superposition theorem, that is only applicable for linear elasticity, basically. Okay. Writing the energy is, it depends, like you can, depending upon the material model, you may have different G or different J, different material properties like G, E. So depending upon that, these may vary. J will depend upon what is the geometry of the body. So depending upon these factors, the energies expressions will be different. It may be different, but in the end, we can find the total energy by adding all the energies. Like we can calculate bending energy, we can calculate the extensional energy, we can calculate the shear energy, we can calculate the torsional energy, and we can add all of them, and we will get the total energy of the body. So in this case, mainly the energy due to the shear force V and moment M is written because we are writing the energy for a beam. Okay, so now we can move on to some of the problem statements. So the question is, think of a rectangular beam as shown. Assume its cross-section to be a circular solid, its cross-section to be a solid circular. Suppose that ring is subjected to equal and opposite forces at A and B. Okay. And they are telling that neglect the energy in the beam's cross-section due to shear force and axial force. The questions they are asking are, by how much will point A and B get closer? So they are applying forces P here at A and B, and they are asking that by how much A and B will get closer. The second question is, by how much will points C and D get apart? So by how much these 2 points will move apart? And the third question is, what is the internal moment in the cross section at C? So we have to find what will be M here. So I think it's clear. So from tutorial 12, we will be doing question number 1 right now. Okay. So here they have given us that we have a rectangular ring Okay. They've applied loads B and B here. This point is A, this point is B. There are 2 points C and D here. This is the length L by 2 and L by 2. And they are asking, the first question is delta AB. So what is the distance between B slash W means between, okay? So I'm using a short form, so I'm just declaring it. The second question is we have to find delta CD. New like reduction in distance, increase in distance between C and D. Increase in distance between C and D. And the third question is moment at cross section at C. So this is what we have. So looking at this question, first thing we should observe that this is a symmetric problem. Okay, so we can actually look at the top part first. This is our A. So we are taking a section at C and D, like those are the midpoints of these limbs. So here the forces and moments will be. Before doing that, we can also observe one thing, that what will be the like deformation in this case. So in this case, our body will deform something. Our body will have some final shape like this. This will be some final shape of the body. This is A, this is B, this is C, and this is D. So the body will deform something like this. And initially it was something like a green line, what I have drawn with the green line, and finally it is what I've drawn using the orange line. Okay, so there is some displacement. So these two displacements. So if we add up these two displacements, we will get what? Increase in the distance between C and D. And if we add these two displacements, we will get that what is the reduction in distance between A and B. So if you look at the problem, it is symmetric. So if we find, if we are able to find out this and this, then we have solved our question number 1, first part and second part. Right, so I should write it A, B, C, D possibly. Will be better. So if we are able to find out what is delta at this point A and what is delta at point C, then we can directly write 2 times delta at A will be the reduction in distance between A and B, and 2 times delta at C will be reduction increase in the distance between C and D. Okay. So if we take a section here between at point D and between point D and C, so the free body will be something like this. Just give me 1 second. Okay. So this is how our free body will look for the half section. Okay. But we cannot get the information about like what is the net force in the horizontal direction. Since it was symmetric, we wrote Vx at both the sides. But what is the value of this Vx? We don't know that. So to find it, we will have to use. So we can do what this problem is also symmetric. So we can like consider this quarter only. We can consider this quarter of the ring only. Okay. So, and also if you look at A, like A cannot rotate. Of course, A can move downwards, but it cannot rotate. If you think about this problem statement. So we can model this something like we can model this situation by something like this in the initial state, of course. Now after deformation, it will look something like so after deformation, it will look something like this, right? So from here, it will go some up. So here the free body will be FC. VC. And this is the moment, so M. Now let us consider what will happen if we had cut at point C. Okay. So because that will give us what will be the value of VC. So if you look at it, this is the upper half and this is the lower half. This is point A, this is point B. B will also be treated like A only, right? Because B and A, they are essentially going through this similar kind of deformation. B is also not rotating. It can only move downwards. So if we fix B, then finally our system will be what? The final stage will be something like this. So this is something like this, right? So from here, if we take a cut section at this point C, our Vx will be in this direction. Suppose if we are assuming Vx to be in this direction, or let me write it as C, Vc in this direction for A, then for B, it will be in the other direction because of Newton's second law. But they are essentially the same Vc should act at the point C because this is a point. So here the same Vc should act. So the only solution is Vc equal to 0. Why? Because from Newton's second law, Newton's third law, each and every action will have equal and opposite reaction. So if we are taking Vc to be in this direction, then in the other direction it will be on B. So I hope this is clear why Vc equal to 0. Okay. So we can remove. And what will be the value of Fc? So from here, we can see that this is also I forgot to write it. So if we write the Newton's second law, we can see that Fd from here plus Fc equal to P. Summation of F y equal to 0. Okay. And we can also do the moment balance. Suppose we are doing the moment balance about this point. So summation of Ma equal to 0. So from there, what we will get? We will get moment at Cm. Suppose I'm assuming counterclockwise to be positive. So moment at C, M plus, maybe I should write it as MC. Here I will write MD, but since the problem is symmetric, so this will be equal to MC. So then the moment because of this force Fc. So Fc into L by 2. Then moment because of Fd. So moment because of Fd is in the counterclockwise direction. Sorry, clockwise direction. So it will come with a negative sign. And this MD is in clockwise direction. So that's why MD equal to minus MC equal to 0. So from here we get Fc equal to Fd. And if we put that here, from to put that here, you will get 2Fc equal to P implies that Fc equal to P by 2. So we can update our free body diagram here. So this was our point A. So now let's so we have a situation like this. Now we will take two cases, okay? We will find what is moment in the vertical part. So initially it was like this, right? So this is our vertical part, and this is our horizontal part. Okay? Now our goal will be what? New goal is to find moment mx in horizontal and vertical part. Vertical part. So let's first do the analysis for the vertical part. So vertical part. Suppose we have made a cut at somewhere at this x. Sorry. Suppose so this is our so this is our case, right? So this is h by 2 and this is L by 2. So remember that. So for vertical part, this is our x. Suppose we have made a cut at this x. So our FBD will be what? This is our FBD. So from here we get V equal to 0 because VC equal to 0. Okay. And Mx equal to, if we do the moment balance and assuming So what we will do summation of Fx equal to 0. So from here V equal to minus Vc. This will be equal to 0. Summation of M equal to 0. And I'm assuming counterclockwise as positive. So minus Mx so minus Mx plus Mc plus Vc into X equal to 0. So Mx is Mc plus Vcx. So this is the vertical part. For horizontal part, let's keep it as Vc minus Vc right now. For horizontal part, what will happen? We have something like this. Our X will be somewhere here, and we are making a cut here. So our final FBD will be, since this is this has the negative normal direction, so our moment will be in clockwise direction, and our shear force will be in the negative direction. Okay. Here actually I have made one mistake. The direction of shear should be in the opposite direction because this is the negative normal face. Here V equal to Vc. And there is some other force here. Okay. Here we have Fc. We have our moment mc and Vc equal to 0. So if we do summation of moment equal to 0 for this case, and this length is x, this is x, right? So summation moment equal to 0 for this case, here we will have minus mx because we are assuming counterclockwise to be positive, plus mc plus fc into x. So this is the force which is acting. So this distance is x. This is h by 2. So fc into x plus vc into h by 2. This should be equal to 0. So from here we get mx equal to mc plus fcx plus vc into h by 2. Okay. So we have found out the moment in the vertical part and top part. Now we need to write the total energy due to bending. So total energy due to bending will be what? Also, one more thing, there is one thing like mentioned in the question that we have to neglect the energy due to shear force and axial force. OK, that's why uh, we will not be considering the energy due to this V or any axial force. We will just write the energy here with respect to because of bending only. Okay, so this is given in the question. That's why we are doing it. So the total energy will be only due to the bending moment. But this bending moment itself is a function of MC, FC, and BC. Right? So we have to so we are showing here in the arguments FC, VC, and MC. Okay. Now the interesting part comes because we have two different kind of moments in the horizontal and vertical surfaces, vertical limbs. So we will have two integrals here. So first we will write for vertical part. So here the moment due to vertical part will come. So what was it? It was MC plus VC into X, right? So the energy due to bending is M square by 2EI. So that is what I'm replacing here. And for the horizontal part, we are moving from 0 to L by 2. The bending moment of the horizontal part as calculated is MC plus FCX into VCH by 2 whole square by 2EI dx. Right? Now this is the total energy. Keep in mind we have found few things. VC equal to 0, FC equal to P by 2, and MC equal to MC. So first we will find what is the value of MC. Okay. So how do we find the value of MC? Now question is, how do we find, this is unknown right now, unknown right now. Unknown right now. How do we find the value of MC? This will even solve, this will help. This is like question number C, but you have to find it first. So we know that there is no rotation at point C. This means what? This means theta C equal to 0. And what is theta C? Theta C equal to del E upon del MC. Equal to 0. So we have the energy expression here. We know that if we differentiate it with respect to MC, we will get theta C, and we know that it will be 0. So what we have to do, we have to differentiate this energy equation and put and equate it to be equal to 0, where FC is P by 2 and VC is 0, right? So let's do that. So del E by del MC will be what? So the integral 0 to h by 2. This will, the upper part will be differentiated with respect to MC, so it will come to be 2 times MC plus VCX into 1. So this will be gone by EI 2EI plus 0 to L by 2 2 times MC plus FCX plus VCH by 2 by 2EI. and this should be equal to 0. So we know that VC equal to 0, right? And FC equal to P by 2. So we'll put it here and we will get. So we can actually remove this 2EI 2 also, because EI, they are independent of X in this case. Suppose if EI depends upon X, then we cannot take them out directly. But here, since E and I, they will not depend upon X, so we will remove them and we can remove the constants also. So we have 0 to H2 MC dx plus EI equal to constant plus 0 to L by 2 MC dx MC plus FC x dx equal to 0. So from here we will have MC into H by 2 plus MC into L by 2 plus FC into x square by 2, 0 to L by 2 equal to 0. So MC into H plus L plus FC into L square upon 4. So we will have MC equal to minus FC upon H plus L into L square upon 4. Now we can replace FC by P by 2. So we will have the expression of MC minus PL square upon 8 into H plus L. So this is the value of MC. So we have solved part C. Part C done. Now we have to find the reduction in the distance between A and B. We have to find what is the reduction in distance between A and B. And to do that, how do we do that? To find reduction in distance between A and B. We will have to do del E upon del FC at VC equal to 0, FC equal to P by 2, and MC equal to what we have found here, minus PL square upon 8 into H plus L. So this is what we will have to do. So again, since we already have the expression for E, so we have to right? It will be off. So we have to first differentiate this part with respect to FC and this part with respect to FC. So we can see that if we differentiate the first part with respect to FC, it will be 0. So FC will come from the, so the contribution will come from the second part only. So it will be 0 to L by 2. Two times MC plus FCX plus VC into H by 2 upon into X upon 2EI. So this will be equal to delta AB by 2, right? This is delta AB by 2. And why are we able to write it as del E by FC? So the amount point C will move. Okay. The amount point C will move in the vertical direction. That is the deflection of this point A. That's why we are able to do that. Okay. So anyways, moving forward, this will cancel. We can take 1 by EI outside. And we can also do VC equal to 0. So we have essentially 0 to L by 2 MCX plus FCX square dx. So delta AB by 2 is 1 upon EI into MCX square upon 2 plus FCX cube upon 3. 0 to L by 2. So this is 1 by 4 EI L square 1 by 4 EI MC plus FL by this is what you will get finally. Okay, so delta AB will be 2 times L square upon 4 EI into MC upon 2 plus FL upon 6. So this is L square upon 4 EI into MC plus FL by 3. And we can replace MC now. So del AB equal to L square upon 4 EI into minus PL upon H plus L plus P by 2 into L by 3. It is minus PL square by 8H plus L. Okay, so we can take PL common also. So it will become PL cube upon 4 EI. We can take PL by 2 common actually. So PL cube upon 8 EI into minus L upon 4. So this is the final solution. Okay. So this is delta AB. Now to find the increase in distance, between C and D, we have to do delta CD by 2 equal to del E upon del VC at C. Okay. So here VC equal to 0, FC equal to P by 2, and MC equal to minus PL upon 8H plus L. So again, we will, let me copy this. Save this also. So this is the total energy, right? So we will have to differentiate this total energy with respect to VC. So del E upon del VC is so this is the differentiation of E with respect to VC. And we will have to put VC equal to 0. So this will go away. FC will be equal to P by 2. So our equation essentially reduces to, I'm taking 1 by EI common from both, MC x dx plus 0 to L by 2, MC h by 2 dx plus 0 to L by 2, FCx h by 2 dx. So delta CD upon 2 is MC x square upon 2, 0 to h by 2, plus MC h by 2 into x from 0 to L by 2, plus FC h by 2 into x square upon 2 from 0 to L by 2. So this 2 will cancel. So we have delta CD equal to MC h square upon 4 plus MC HL upon 2 plus FC HL square upon 8. Okay, so here substitute the values of MC, PL upon 8H plus L. I have missed 1 by EI. So remember to include 1 by EI, which we had taken common, minus PL upon So delta CD is minus P upon 16 into LH. LH is common. Here it will be 1 by EI. So from here we will have 1 minus H upon minus H upon 2 times H plus L. From here I will have minus L upon H plus L. From here I will have plus it should be PL square. Why am I making this mistake again and again? So solve this and we will get PLH upon 16 EI into minus HL plus minus 2L square plus L into H plus L on 2 into H plus L. So delta CD is minus PLH upon 1632 EI into H plus L. From here we will have minus 2L square minus HL plus HL plus L square. This will cancel. So this minus, and from here I will have minus L square. So PL cube H upon 32 EI into H plus L. This is delta CD. So this is the method to do it. If I have done some calculation mistake, you can recheck it. But this is the way to do it. You have to find the differentiation of E with respect to V, and after that you have to calculate the different values. So hopefully I've not done some calculation mistake here. Anyways, so let's move on to question number 2. So question number 2 is using energy method, determine the vertical deflection of point B under the action of load W. So this is point B and the horizontal reaction force at B. What will be the horizontal reaction force at B? The end of the B is free to rotate. So here rotation is free, but can move in only in the vertical direction. So the body is allowed to move in the vertical direction. Consider all forms of energy, that is bending, twisting, stretching, as well as shearing energy. So first, look at this question. At B, there will be only horizontal reaction. Why? Because first of all, it is allowed to move in the in the vertical direction, so there will not be any reaction there, and it is free to rotate at point B. So only horizontal reaction will appear at B. So let's move on to question number 2. Hopefully, I will be able to finish this one. And they have given some dimensions also, right? So they've given the radius of this circular arc to be A. So only horizontal reaction will be there. So RB is like this. Okay. But since we have, and what we have to find, we have to find vertical deflection of point B and horizontal reaction. B. And the second part is horizontal reaction at B. At B. Now, since it is free to rotate at B, MB equal to 0. So this should come in mind. Okay. The moment at B will be 0. And to find the and also the vertical force, it has been mentioned to be W here. They have given that there is some W is here. So what are the knowns? Knowns are W, the dummy load, we will apply dummy moment. Load, we will apply MB to find the rotation. These are known. And unknown is what? Unknown is RB, horizontal reaction. Horizontal, why did I say horizontal? Horizontal reaction at B. This is unknown. And they have told us that use all forms of energy. So they have told all forms of energy. So use all forms of energy. So we need to write the bending energy. We need to write the shear energy. We need to write the torsional energy. We need to write the extensional energy, right? So what will be the steps? We need to find moment. This is m theta. We need to find the shear force. That is V theta. And we need to find the axial force also. Why? Because we will have to write all forms of energy. So we need axial force for stretching. We need shear force for shear energy. And we need moment for the bending energy. So we need to find them. So how do we do that? So we will make a cut. We will from here at some angle theta, we will make a cut. So here we have W, we have RB. Suppose so this will be the moment is in this direction, MB equal to 0. So this makes it as our positive phase, right? So in this case, F theta is in this direction. This is V theta. And this is our moment M theta. So using force balance and moment balance, we shall find M theta, V theta, and F theta. F theta. So what will be F theta? And how do we find it? So let's draw it properly. This is our point B. This is the point where F theta is acting. F theta is acting in the axial direction. Here we have W. Here we have RB. This is the direction of shear V theta. This is A and this is theta. This is what? This is A sine theta. This angle will be theta. This angle will also be theta. Why is this angle theta? Because this is theta, so this is 90 minus theta. This is 90 degree, and here it is in the axial direction. So this whole angle is 90 degrees. So this is 90 minus theta, so this must be theta, right? So let's do summation of F. So let's decompose the forces. Suppose this is this is Y and this is X, or E1 or E2, I will say. Suppose this is E1 and this is E2. So F theta cos theta E1 plus F theta sin theta E2. So if you do the force balance and moment balance, because the time is running out, I will directly write it. You will get F theta equal to RB cos theta minus W sin theta. Okay. You will get V theta equal to RB sin theta plus W cos theta. And okay, I forgot to mention moment here, so I should write. m theta equal to mb minus w into a sine theta minus rb into a 1 minus cos theta. Okay. This will be, and we are writing moment about this point. So suppose this point is, let us assume this point is E. So summation of moment about E equal to 0 will give you this expression m theta equal to this. Okay, because f theta and v theta, they are crossing through this point only. So the moment because of them will be 0. And you can see W is acting here. So the length, the distance of W from point E is a sine theta. So that is here. And the RB is at a distance a, this length is a cos theta, right? So this is a cos theta. And this whole length is this is a. So this will be what? A into 1 minus cos theta. So that is the distance of RB from this point E. So that is written here. And we are assuming counterclockwise to be positive. So if you write that, you will get the result same. So counterclockwise as positive. You will be able to find f theta and v theta if you do the force balance. Over here, summation of force equal to 0. If you do the vector sum, you will get the expression of f theta and v theta. So total energy will be E as a function of FB, RB, and MB. So I will write it as E equal to 0 to 3 pi by 2. Why 3 pi by 2? This theta will have range from 0 to here, 3 pi by 2. Okay. The energy due to XL for F theta square upon 2 EA plus the energy due to CF V theta square upon 2K, the correction factor GA plus M theta square upon 2 EI. Okay. Okay. AD theta. So sir has done this thing in class also, so you can refer why AD theta is coming. This is because the integral was over dx and we convert the length, so it is AD theta. So E equal to 0 to 3 pi by 2. We will replace f theta by RB cos theta minus W sin theta. This whole is square upon 2EA plus RB sin theta plus W cos theta whole square upon 2K GA plus the moment MB minus WA sin theta minus RB into 1 minus cos theta into A. This whole is square upon 2 EI d theta. Okay. Now, if we move to the question, we can see that the end B is free to rotate. It can move freely. It can move only in vertical direction. This means that the end B cannot move in X direction. Okay, so this means del E upon del RB equal to delta of B in horizontal direction. I will say it as delta Bx. That is delta Bx equal to 0. So if we do that, we will be able to find the value of RB. Okay, and we know what? We know MB equal to 0. So after doing this, we will have to put MB equal to 0. Okay, so let's differentiate. So 0 equal to 0 to 3 pi by 2, 2 times RB cos theta minus W sin theta upon 2EA into cos theta plus 2 into RB sin theta plus W cos theta upon 2kGA sin theta plus, here it will be 1 square mistake, 2 times MB minus WA sin theta minus RB into 1 minus cos theta into A. This multiplied by 1 minus cos theta into A. Divided by 2EI, and this is getting integrated over d theta. So from here 2 will cancel and we will have 0 to 3 pi by 2. We will have to put MB equal to 0 also. This will become 0. Oh, 0 to 3 pi by 2. Cancel all these 2's. We have RB. Let's write cos theta as C. So C theta and sin theta as S theta. Okay. Plus so if we solve this, we will get three RB minus 2W upon 4 EA So this is what we will get. So from here we will get RB equal RB into 3 pi upon 4 EA plus 3 pi upon 4 kGA plus A square into 2 plus 9 pi upon 4. This will be equal to 1 by 2 EA plus 1 by 2 kGA. Sorry, it should be with minus sign here. Minus A square upon EA. So from here, we will get RB. Now we have already found what is RB. Okay. Now what we have to do, we have to find the vertical displacement. Okay. So to find the vertical displacement, we will have to do delta V equal to, or maybe delta By, I will write. So this is X, this is Y. Okay. So the vertical displacement is delta By. This will be equal to del E upon del W. So we have to differentiate our energy with respect to W now. So if we differentiate with respect to W, what we will get? We will get del B equal to del E upon del W equal to 0 to 3 pi by 2 into RB cos theta minus W sin theta into sin theta upon EA, the negative sign. So we will have to put MB equal to 0. And we can put RB equal to expression we have found. Okay. So put the expression of RB we have found and integrate. So you will be able to find, you will get the value of delta B. Okay. You'll get the value of delta B. So I hope this question is clear to all of you. Now, this will be probably the last question for today. So we'll try to wrap it up soon. So the question is, for the structure shown, what is the vertical deflection at A? Also determine the ratio of L to R if the horizontal and vertical deflections of the loaded end A are equal. Okay. And P is the only force acting. So they have given you a P which is only acting. They are telling that what will be the vertical deflection at A. So we have to first find the expression of vertical deflection at A. Then they have told that the axial, basically the horizontal as well as the vertical direction, in the vertical direction, whatever deflection is happening, they are equal. So what will be the value of L by R? Okay. So question number 4. Question number 3 has already been done in the class. So it will be better if I do the question which is not covered. So the P is applied here. This is a semicircle, I guess. Yes. The semicircle, this is point A. This is length L. And this is radius R. So question 1 is, so let us assume this is X and Y. Okay. Question 1 is find delta Py and delta Px. Though they have told us to find delta Py, so I'll just write delta Py. And the second part is find L by R if delta Py equal to delta Px. Okay. So till now what we have done, if you remember, we first write the energy of the system, total energy. So what will be the steps? Steps is first identify what we have to find. So you can see that from question number 2, we need to find delta Py as well as delta Py. We need to find delta Py as well as delta Px, right? So to find delta Py, we already have our force P in the vertical direction. We already have that. So here we already have our vertical direction force, right? So we already have our vertical direction force here. And so we will be able to find delta Py. But to find delta Px, we need one horizontal force also, right? But it is not given. So we will have to assume one dummy force in the horizontal direction. And the value of that force will be F equal to 0. And after calculating the energy, when we differentiate to find delta px, we will have to differentiate with respect to that dummy force, and we have to set the value equal to 0 at that moment. I hope you are able to understand this, that first we need to write the total energy. After writing total energy, if we want to use Castigliano's first theorem, we already have our vertical force P. So we will be able to find delta Py, but we will not be able to find delta Px because there is no force in the x direction. So for that, we will need to apply a dummy force Fx equal to 0. Okay, so that is what I will do now. I will apply a dummy force here, Fx equal to 0. Or simply F, I will write F equal to 0. Okay, dummy force. So remember these steps. First you have to First you have to write all the energy. So to write the energy, you need a dummy force because we have to find the deflection in the x direction. Okay. So now we will have to find the sectional forces and moments at an arbitrary section. So we can take two different cross sections, one at angle theta. So let's see. I will redraw this. So we will take one section here at some angle theta. Okay. So this will be one section and the other section will be okay. This point is A. So this is A. From here, we will take one section here. So first, let's find the sectional force there. This is point A. This will be M theta. This is our B theta. And this is F theta. This is our P here. This is our F here, F equal to 0. And we know that this angle is theta, this is R, and this is R. Okay. So how do we calculate the bending moment? So summation of moment equal to 0. We are assuming counterclockwise to be positive. This is positive. So we can write the moment about this, suppose this point is, the point of cut is B. So this is B. So summation of moment about B is 0. So what will happen? Minus m theta. So here it will be minus m theta. Okay. Plus the distance of force F will be what? So we have a triangle like this. We have an arc like this. Alright. Sometimes my system starts doing weird things. Suppose this is our theta. Okay. Oh, I saw. This is theta and this is r. So this distance is r sine theta. And this distance is r into 1 minus cos theta. So the moment due to this F will be vertical distance of this F from this point B. So F into r sine theta plus P into 1 minus cos theta into r. And this should be equal to 0. Now the moment due to P will be in the clockwise direction. Yeah, so it should come with a negative sign. So here it should be minus P. So m theta will be P into 1 minus cos theta into r minus FR sine theta. So this is the expression of FR sine theta. So this was the first cut which was made at this point. Now we want to the other section will be on this vertical straight part, and here let us assume we are making a cut here. Okay, so we will have to draw the free body diagram. Maybe I can move this one here. So this portion, which is the vertical part, we can have a cut there. And for this part, the free body diagram will be something like this. So here we will have two different things. Okay. So here let's have, for this part, let's have a cut here also. So we are having cuts at two different points for this horizontal, for this vertical part. So let us assume this point is D. So for A and D, the expression for m theta will be like this, right? So at D, the Direction of shear force is V theta is this. Maybe I should draw it again. Oh, guys. So this is the like the direction of forces and moment at point D. So by Newton's third law, the forces direction, the direction of movement and forces will be in the vertical strip will be uh, in the vertical limb will be in the opposite direction, right? So F theta, V theta will be something like, yeah. This will be V theta and the moment will be in this direction. Sorry, in the opposite direction, because so this will be the direction of moment m theta. And from below, we will have Fx, Vx, and Mx. So what is m theta here? M theta is m theta at theta equal to pi from the curved portion. Curved portion. So I'd like to reiterate what I have done till now. So basically, the moment we have to find the moment in this curved portion. In this curved portion, we have to find the moment, and we have to find the moment in this vertical section, right? So I have made different cuts here. So for curved section, this analysis was done, whatever I have shown here. For the horizontal section, we are doing this analysis here. We are making cuts at D and some other point here at C. OK, now at D, we know the value of moment. It will be the moment expression we have already found here, m theta. So we will have to put pi, theta equal to pi here, and we will find the moment equation at D. OK, so m theta at D. Let's write. This is m theta at D. So what is this expression? M theta at D equal to P into 1 minus cos pi into R minus FR sin pi. So sin pi is 0. So m theta at D is P into 1 into minus 1 R. So this is 2PR. OK. And what will be V at theta? So from here, we have to also find V theta. OK, so the expression of V theta will be found from where? V theta and F theta can be found by doing summation of F equal to 0. OK, so what in the horizontal direction, the forces will be. So let me draw something here. This angle is theta. So this will be, this angle will be 90 minus theta. So F theta sin theta minus So it should be minus f theta sin theta plus b theta cos theta equal to 0. So from here, v theta equal to f theta tan theta. Okay. This is summation of fx equal to 0. Now in the vertical direction, f theta cos theta plus v theta sin theta minus p equal to 0. So from here we will get f theta equal to p minus p by cos theta minus v theta into tan theta. So putting this here, we will get v theta equal to f theta, p tan theta upon cos theta minus v theta tan square theta. So v theta is p tan theta by 1 plus tan square theta cos theta. And we know that 1 plus tan square theta is sec square theta. So v theta will become v theta equal to p tan theta upon sec theta. And this is equal to p sin theta. Here instead of 0, we should write f because we don't want to. Because later on we need because later on we need to differentiate with respect to this f, right? So we need this f. Anyways, so we have to, so bending moment in the straight part, bending moment in the straight part about point C. So we will do summation of MC equal to 0 at, so about point C. And we are assuming counterclockwise to be positive. Okay, so minus mx plus m theta minus v theta into, this is x. Sorry, this is y. Because it was in the clockwise direction. So here we will get mx equal to m theta minus v theta into y. So mx equal to Oh, I've missed a negative sign here. Should be plus for sine theta. So here it will be minus. Here it will be plus. So there will be a minus sign here. Okay. So you can also check these calculations which I have made. Okay. So we'll put minus 2 PR. Let me check. So minus f theta sine theta. Minus f theta sine theta plus b theta cos theta. B theta cos theta plus f equal to 0. So this is correct. B theta equal to f theta tan theta. Okay. It should be sec theta. Then here we have f theta cos theta vertical direction, v theta sin theta in the vertical direction, minus p equal to 0. This is correct. So f theta cos theta will be p by cos theta minus v theta by tan theta. So this is also correct. This was summation of fx equal to 0. This was summation of fy equal to 0. Okay. So from here I have got p by cos theta minus v theta tan theta equal to f theta. Okay. So while putting here, we will have p by p tan theta by cos theta minus v tan square theta minus f sec theta. So v theta at theta equal to pi is p into sine minus f into cos pi. So this will be equal to f. So this is the expression for my. I'm sorry, I'm exceeding today because I made a calculation mistake. I'm so sorry for that. But now what we have to do is now we will have to write the total energy. Okay. So total energy is 0 to pi m theta square upon 2ei into r d theta plus 0 to L my square upon 2 ei into dy. So what are the steps? We have to consider the circular part or the arc part first. Then we will have to consider the vertical part. And for circular or for the arc, we have to find the expression of m theta and v theta. Then we will find the values of m theta and v theta at this point D, and point D means theta equal to pi. So that is what has been done here. And after that, for the vertical part, we will cut a section at C, and we will also detach this vertical part from point D. So we will have our reaction forces like this, and we will calculate the moment at C. Okay, so this is the moment we have calculated, and we have found it to be minus 2pr minus Fy. Now the total energy we have written like this. We will replace the expressions of m theta. So the expressions of m theta is minus pr into 1 minus cos theta plus fr sin theta whole square upon 2ei and this is integrated over theta, and there will be one more r. So here it will be r d theta plus the expression for my is minus 2pr minus Fy into dy, and here it will be 2ei. Okay, should be square. Now to find the vertical displacement, do del E upon del P. Okay, del E upon del P at f equal to 0. This will give you equal to delta Py. Okay, so this will give you delta Py. So do that, and you will find that delta Py equal to PR square upon EI into 3 pi r upon 2 plus 4L. Okay, so this is your delta Py. Next step is, so this is if you differentiate E with respect to P and put F equal to 0, you will get delta Py after integrating. And to find horizontal displacement, do del E upon del F at F equal to 0. Okay, so this will give you delta Px. Okay, and so similarly, follow the steps we have followed for other problems, and you will get delta Px equal to PR upon EI into minus 2r square plus 2l square. So this is part A is done. Part A of the question. And from part B, so now what you have to do now, equate part B. Now equate delta Px and delta Py. So if you equate them, so delta Px equal to delta Py implies that PR upon EI into 2l square minus 2r square equal to PR square upon EI into 3 pi r upon 2 plus 4l. Okay, so P will cancel, EI will cancel, but R will go away. So from here you have 2l square minus 2r square equal to 3 pi r square upon 2 plus 4L r. So divide both sides with r square. So this will be L square minus r square equal to 3 pi by 4 r square plus 2LR. And you solve this, you will get so divide by r square. Okay. So you will get L upon r square minus 1 equal to 3. Minus 1 plus 3 pi by 4 minus 2L by r equal to 0. So you have a, so let L by r is rho. So you have a quadratic equation rho square into 2 rho square minus 2 rho minus 3 pi by 4 plus 1 equal to 0. So solve for rho. So for quadratic equation, what will be the solution? It will be 2 plus minus square root of b square minus 4ac. So b is 4 plus 4 into 3 pi by 4 plus 1 upon 2a. So this is 1 plus minus square root of 1 plus 3 pi by 4 plus 1. So the answer rho is 2, 1 plus square root of 2 plus 3 pi by 4. So you can check for the calculations. If I've done some calculation mistakes, you can correct it, but this is the way to do it. So if you follow these steps, you will be able to find the answers. So thank you all of you for joining. If you have any doubt, you can write in the chat, you can unmute yourself and you can speak. If none of you have any doubt, then I will end this meeting. Okay, since none of you have any doubt, I will be ending this meeting. We will meet again for week 12 in the next week. And that will be on, I think, theory of failures. So I hope to see you all again next week. Thank you all of you for joining. Bye bye. Have a great day.